Data link layer, layer 2. This is where the broadcast domain is limited to. Broadcast domain is a group of nodes that can receive each other's broadcast messages segmented by a router. And then a collision domain is a group of nodes that share the same media segmented by a switch. I think we'll go into later like the differences, in fact I know we'll go into later, the differences between like a switch and a hub and a switch and a bridge, and why why a hub is a dumb device and a switch is able to actually segment out the collision domain so you don't have packets colliding with each other. Whenever you've got just like a hub, you have to have CCNA CD collision carrier sense multiple axis and collision detection, which is basically like a little algorithm that whenever you've got all of these nodes, a bunch of PCs in the same collision domain, anytime data like sends at the same time and happens to hit each other, they all have to go through this little backup algorithm where they all stop transmitting for a certain amount of time, or actually it's a random amount of time based on an algorithm, and then one will start transmitting, and you have to keep going through this over and over and over in a collision domain. A switch and a bridge corrects that, but all of this stuff is still in the layer 2 area. Let's see, there's two actually sub-layers to the data link layer: the media access control layer and the logical link control layer. The MAC layer, you guys, especially working in the NOC, you've probably seen this printed on the back of cable modems and routers and all that kind of thing. It's a hard-coded address on the NIC. Every NIC has one. It's 48 bits, zeros and ones, 12 hexadecimal digits, 0 through 9 and A through F. We'll get into hexadecimal, like I said, chapter 5, but it's basically a collection of 4 bits. You're counting up to 16, or actually 0 through 15. Since you can't, you're trying to keep it as a single digit, it's going to go 0 through 9 and A through F. First 6 hexadigits identify the manufacturer. So like if you guys go to a MAC address cross-reference site, there's a bunch of them on the internet, and you plug in a MAC address, what it does is it strips off those first 6 digits of the hex identifier of the MAC address, and it can tell you like which manufacturer those are registered to. The last 6 hex digits on that MAC address are specific to that device. So a manufacturer will get their identifier, their 6 hex digits, and then each device that they create for however long of a period will segment those out. Under the MAC layer, you've got the logical link control layer, LLC. This complements the MAC layer with framing, error, and flow control. And then the physical layer, as we talked about before, the physical media data will traverse. The physical medium. That's actually, I need to correct that. The physical medium that data will traverse, specifications, voltage, wire speed, and pinout capability of sending and receiving signals. So physical layer can be wireless, it can be an Ethernet cable, etc. Okay, so on top of the OSI model, we've got the TCP/IP model as well. This was developed by the Department of Defense. It actually lines up pretty well with the OSI model, and I know that I had a couple of questions on the TCP/IP model.
I'm so sorry.
Actually,
vibrate, baby. Vibrate.
The one question I can specifically remember having was a simulation where they would have the application layer or vice versa lined up like all right, and then you had to match up like the layers of the TCP/IP model where the OSI model links up at. So on the TCP/IP model, the 5, 6, and 7 on the OSI model are all broken down and just listed as application. Layer 4 is the same, so that's easy to remember. It's transport on both sides. And then the layer 3 is listed as the internet layer rather than network layer. These are all still doing the same functions. All of the protocols we talked about in the OSI layer, they all fit into their respective layer on the TCP/IP model. And then the bottom 2 layers of the TCP/IP model are also squished, or from the OSI model are also squished in the TCP/IP model to the network interface layer. So physical medium and data link is all just network interface on the TCP/IP model. This is just like the OSI. It's just memorization. You're going to have to memorize it. Oh, and then this is kind of a, I guess I probably had some questions on this. This is Cisco's 3-layer hierarchical model of building networks. Starting from the bottom, you have your access layer, which are usually like dumb switches where all of the individual PCs and stuff connect. And then right above that, you'll have your either a router or smarter switch that kind of all of the individual. This kind of model is really meant for like a larger network. To me, they can kind of compress like part of this into 2 layers. Like most networks, unless you're talking about like a really high-end headquarters or a campus network or something like that, the core layer and the distribution layer are probably going to be compressed into a single layer. But Cisco's ideas for redundancy and making sure you have multiple failovers and that kind of thing has this 3-layer hierarchical model where you have an access layer, a distribution layer where all the individual access switches connect to, and then a core layer that hires the higher level functions. And part of this too is like they're worried about like processors on individual routers being held down because they're worrying about doing too much at one time. So once again, this is not a model for like in our field, an individual restaurant franchisee. This is like a headquarters kind of thing, and a big headquarters at that. And that's all there is to Chapter 1. Any questions on that stuff? Like I said, it's a lot of memorization, but you're just going to have to kind of read it and memorize it. So any questions pertaining to the actual material, though? And the crickets are quiet.